Try to hold a snowflake in your bare palm. You feel it, you see the detail, and then, without warning, it collapses into a wet, ordinary drop. Now imagine that snowflake is a calculation. If the universe runs on quantum rules, why is the most natural computation so hard to keep intact long enough to use? I'm Rowan K. Mercer, and this is the Science Audit. Today we're stress testing a phrase you've heard everywhere. Quantum advantage. Not as hype, not as a meme, but as a measurable claim. Because the promise is enormous: new medicines, new materials, new chemistry, maybe cleaner industrial processes, and definitely a revolution in cryptography. And the risk is also enormous, confusing a delicate physical phenomenon for a guaranteed technological miracle. Here's the core question that should bother you in a productive way: if reality itself is quantum, why can't we easily build quantum machines that consistently outperform classical ones? And what would it actually mean for your life, your privacy, your health, your energy costs, your sense of what's predictable, if we could? To answer that, we need an audit standard. We're going to separate three things that constantly get blended together. First, what physics allows in principle. Second, what engineering can do in practice, under noise, budgets, and time. And third, what counts as an honest advantage compared to the best classical methods, not compared to a strawman. And I want to put one sentence on the table early, because it will keep us sane. A quantum computer isn't a faster calculator. It's an interference engine. It computes by choreographing waves of possibility so that wrong answers cancel and right answers reinforce. But interference only works if the phase stays coherent, and the universe is loud. So let's build intuition first. No mysticism. No magic. Just the strange, beautiful accounting system that nature actually uses. When people say, a qubit is 0 and 1 at the same time, it sounds like a riddle. The more honest picture is this: a qubit is like an arrow that can point anywhere on the surface of a sphere. North is what we label 0. South is what we label 1. But the arrow can point somewhere else, say, halfway between north and south. That somewhere else is not a third value. It's a recipe for probability, plus something extra that classical bits don't have: phase. Phase is the part that makes quantum computing feel like music rather than arithmetic. If amplitude is volume, phase is timing. Two notes can add into something louder, or they can interfere and cancel into near silence, depending on whether they line up. A qubit carries this timing information in its state. And a quantum circuit is, in a very real sense, a composer. Now, superposition. Here's a metaphor that doesn't oversell it. Think of superposition as bookkeeping, not of what is, but of what could be, with weights and phases attached. A classical bit is a single line in a ledger: it's 0 or it's 1. A qubit is a two-line ledger that keeps both entries, with complex number weights, until you force the issue by measuring. Measurement is where the universe cashes the check. You don't peak at a qubit's full state. You sample from it. The ledger collapses into one outcome, and you get a classical bit as the receipt. And here comes the first uncomfortable question: if measurement collapses the useful quantum information into a single classical result, how can that ever help you compute? Answer: you don't try to read the whole ledger. You use interference to sculpt the ledger so that, when you finally sample, the right answer shows up with high probability. The entire game is to reshape a probability landscape, from something flat and uncertain into a sharp peak over the answer you want. Picture two sets of ripples moving across a pond. Where crest meets crest, you get a taller wave. Where crest meets trough, the surface calms, cancellation. Quantum algorithms are basically that, but in an abstract space of possibilities. They set up a vast interference pattern so that the paths leading to wrong results cancel out, and the paths leading to correct results add up. And that brings us to entanglement, the word that gets used like glitter. Let's strip it down. Entanglement is a pattern of correlation that cannot be reduced to independent local stories. It's not just two things are connected. It's the system has information in the relationships, not in the parts. A classical analogy is a pair of gloves in a box. If you open one box and find a left glove, you know the other is right. That correlation is boring because each glove had a definite identity all along. Entanglement is stranger. It's as if either box contains a definite glove until you open one, and yet the outcomes still coordinate in a way that defies any simple hidden script. The correlation is real, measurable, and mathematically irreducible. Why does that matter for computing? Because entanglement is a kind of compression. Certain structures that would take an astronomical amount of classical memory to represent can be represented compactly in a quantum state, if you can control it. It's like writing a symphony as a score instead of recording every possible performance note by note. So, qubits carry amplitude and phase. Circuits manipulate these like rotations of that arrow on the sphere. Entanglement lets the system represent relational information compactly. And the algorithm's job is to engineer interference so that when you finally measure, you're not rolling fair dice, you've loaded the dice using physics. Now let's audit the word advantage, because this is where the conversation usually derails. Quantum advantage means a quantum device completes a well-defined computational task using fewer resources, time, energy, hardware, than any known classical method, under a clearly stated cost model. That's the adult definition. But people often mean quantum supremacy, which is a narrower milestone, doing something that is classically infeasible to simulate, even if the task itself isn't useful. Supremacy is like climbing a mountain to prove you can survive the altitude. Advantage is building a road that people actually use to get somewhere they need to go. And then there's fault tolerance, the phrase that sounds bureaucratic but is actually the heart of the matter. Fault tolerance means operating below an error threshold so that error correction can suppress logical errors exponentially with overhead. Translation: if your hardware is good enough, you can stack protective layers so errors don't just accumulate, they get actively pushed down as the computation grows. Here's a question you should keep asking as we go: are we talking about a stunt, a tool, or an industry? Because those are three different targets, and the honest metrics are different for each. Let's talk about speedups, what quantum computers are actually good at, and just as importantly, what they are not good at. The myth is that a quantum computer is a universal accelerator, like strapping a rocket engine onto every piece of software. Reality is narrower and more interesting. Some tasks see no quantum benefit at all, or they're dominated by data movement, and error bars and messy real-world constraints. Some tasks see polynomial speedups, nice, meaningful, but not world-shattering if the constants are ugly. And a few tasks have dramatic theoretical advantages. The celebrity example is factoring large integers with Shor's algorithm, which threatens widely used public key cryptography. Another major domain is quantum simulation, using controllable quantum systems to imitate other quantum systems, like molecules and materials, where classical simulation hits a combinatorial wall. But notice what that means. Quantum computing is not faster at everything. It's faster at specific classes of problems where interference and entanglement let you traverse structure that classical computation has to grind through. So I like to sort claims into three categories. Category 1, demonstrable speedup on a contrived task, useful scientifically, because it stress tests hardware and theory. Category 2, practical advantage on valuable tasks, something a working scientist or engineer would pay for because it changes outcomes or costs. Category 3, fault-tolerant, scalable advantage, the kind that survives real-world error rates, scales to large problem sizes, and becomes a stable platform. If you've ever felt whiplash from quantum headlines, it's usually because the headline is describing Category 1, while your imagination hears Category 3. That gap, between what was done and what you thought was promised, is where hype lives. Now we slow down, because we're approaching the brutal core of this entire field. If quantum computing is an interference engine, then coherence is the fuel. Coherence is the ability of those phases, the timing relationships, to remain well-defined long enough for the algorithm to finish composing its pattern. And decoherence is what happens when the universe steals the timing sheet music. Decoherence isn't a bug in the code. It's physics. Every stray photon that bounces the wrong way, every vibration that nudges an atom, every microscopic electric field fluctuation, each is a tiny interaction that acts like a partial measurement. It leaks information about the qubit into the environment. And when the environment learns, even a little, the qubit forgets who it was. Here's an image. You're trying to hear a whisper across a stadium during a storm. The whisper is your quantum phase. The storm is thermal noise, electromagnetic interference, material defects, cosmic rays, imperfect control pulses, reality doing what reality does. Building a quantum computer is like building a cathedral around that whisper, not to amplify it, but just to keep the storm from overriding it. And quantum errors are nastier than classical errors in one key way. In a classical computer, the basic failure mode is a bit flip, 0 becomes 1 or 1 becomes 0. In a quantum computer you can get bit flips, but you can also get phase errors. Remember that arrow on the sphere? A phase error is like the arrow quietly rotating around its axis. The probabilities might look fine if you check in the wrong basis, but the interference pattern later will be ruined. And this leads to a paradox that feels like a dead end until you learn the trick. The no-cloning theorem says you can't copy an unknown quantum state. We don't know how. Nature forbids it. So you can't do the obvious thing classical engineers do, make backups of your data and restore from a clean copy. So how does quantum error correction work at all? How do you protect something you can't copy, and can't even directly observe without destroying? The key idea is almost philosophical. You don't measure the data, you measure the damage. You perform what's called syndrome measurement. You entangle your data qubits with helper qubits, ancillas, in such a way that certain collective properties reveal whether an error occurred, without revealing the actual computational state. It's like checking whether a violin string went out of tune without listening to the melody being played. In practice, you encode one logical qubit, the qubit you actually care about, across many physical qubits, the imperfect hardware units you can build. And you constantly run error detection cycles, like a heartbeat monitor, catching and correcting before small mistakes cascade into nonsense. Now comes the part that sounds like science fiction until you do the arithmetic and realize it's just expensive. The overhead can be enormous. Depending on your physical error rates and how long you need the computation to run, one logical qubit might require hundreds, thousands, or in extreme projections, even millions of physical qubits. Not because the idea is wrong. Because the universe is loud, and you're trying to hold a snowflake. This is why the millions of qubits headlines need immediate clarification. When you hear millions of qubits, ask, physical or logical? Physical qubits are like raw bricks. Logical qubits are like finished rooms you can actually live in. There is, however, a genuine beacon of hope in the theory, the threshold theorem. It says that if your physical error rate is below a certain threshold, then in principle you can scale up fault-tolerant computation. Errors can be suppressed exponentially as you add more redundancy. But this matters possible is not the same as cheap. You can cross the threshold and still face an engineering Everest. Your refrigerator has to stay cold. Your control electronics have to stay stable. Your fabrication has to stay uniform. Your decoding algorithms, the classical software that interprets the syndrome measurements, have to run fast enough to keep up. A quantum computer, ironically, leans on a lot of classical computation just to remain quantum. And that brings us to the era we're in right now, often labeled NISQ, noisy intermediate-scale quantum. Translation: we can build devices with tens to thousands of physical qubits, but they're noisy, and deep circuits accumulate errors too fast. So what can NISQ devices do? They can do interesting physics. They can explore small chemistry problems. They can act as testbeds for control, calibration, and error mitigation techniques. They can sometimes show special-purpose wins where the question is tailored to what the hardware can actually maintain coherently. But broad, general advantage is constrained by depth, noise, and verification. Which raises one of the strangest practical issues in this whole story. If a quantum device claims it did something you can't classically simulate, how do you check it without just trusting it? That's the verification problem, and it's not a philosophical gotcha. It's an operational question about trust. Science is built on reproducibility and independent checks. But if the entire point is that classical machines can't efficiently reproduce the output distribution, you need clever statistical tests, cross-checks, and sometimes interactive protocols to validate that the device behaved as claimed. And there's another question that's even more grounded: advantage versus cost. If your speed-up requires a dilution refrigerator, a warehouse of control equipment, extreme power draw, and a small army to operate, and the classical alternative runs on a cluster you already own, then the advantage might evaporate in the real economy. The stopwatch is not the only metric. So when you hear quantum advantage, here's the audit filter I want you to apply automatically. Advantage at what task? At what scale? With what error model? Compared to what best-known classical algorithm? Because classical algorithms are not standing still. The moment a quantum team announces a benchmark, classical teams often respond with better simulation methods, smarter approximations, hardware acceleration, or tighter cost accounting. The frontier moves because both sides are clever. Now let's zoom out, because the technical story points at something bigger than hardware roadmaps. Quantum computing is a mirror. It reflects a deep truth we often forget in an age of abstract software: information is physical. A computation isn't just math in a vacuum. It's a physical process that must obey thermodynamics, noise, causality, and quantum laws. A transistor isn't a 1, it's an arrangement of matter that we've trained to behave reliably enough that we can pretend it's a 1. A qubit isn't mysterious, it's a fragile physical system whose phases we're trying to steer like a tightrope walker in high wind. And that reframes what progress means. Progress is not just more qubits. It's lower error, better connectivity, more uniform devices, better calibration automation, better decoders, better algorithms that need fewer layers of operations to achieve the same effect. Here's a useful gut check: if someone only talks about qubit count, they're grading the orchestra by how many instruments are on stage, not by whether they can stay in tune for the full symphony. So what are the likely early wins, if we keep our feet on the ground? Quantum simulation is the most honest candidate. Chemistry and materials are quantum at their core. If you can directly simulate electron interactions in molecules that matter to batteries, catalysts, fertilizers, pharmaceuticals, there's a path to real impact. Not instant cures. More like better leads, fewer dead ends, and new compounds we couldn't confidently predict before. Another possible area is niche optimization and sampling problems, but with careful caveats. Optimization in the real world is messy. Noise, constraints, and changing objectives can swamp theoretical speed-ups. But certain structured problems, especially where you can tolerate approximate answers or you can embed the problem naturally in quantum hardware, may show practical benefits. And what about the claims that a quantum computer will accelerate general AI, or solve every computational bottleneck? That's where the audit gets strict. There is no general theorem that quantum computers speed up all of machine learning. Data loading can dominate. Many ML workloads are limited by memory bandwidth, not raw arithmetic. There may be subroutines with quantum advantage, but turning that into an end-to-end product advantage is a separate, hard problem. Now we have to talk about cryptography, because this is where quantum computing touches your life even before the hardware arrives. Shor's algorithm, on a sufficiently large fault-tolerant quantum computer, could break widely used public key cryptosystems like RSA and ECC. That doesn't mean your phone is doomed tomorrow. It does mean the world is already migrating toward post-quantum cryptography, new schemes believed to resist quantum attacks. And there's a very present-day risk called harvest now, decrypt later. An adversary can store encrypted data today, medical records, diplomatic cables, corporate secrets, and wait for future quantum capability to decrypt it. So the timeline uncertainty is not comforting. It's a reason to upgrade early when the information needs to stay secret for decades. Notice what's happening here. Quantum computing isn't just a gadget. It's a stress test of trust infrastructures. It forces governments, companies, and individuals to ask, what does it mean to make a promise of privacy that lasts? And that returns us to the deepest layer of the story, the one that feels almost spiritual if you let it, but will keep it honest. The profound mystery isn't whether quantum computers will exist. Small ones already do. The mystery is what it means that the universe permits them at all, but only if we learn to shelter coherence like a flame in a storm. Because here is the weird, human-shaped truth. The laws of physics offer us this astonishing computational resource, interference across vast spaces of possibility, then immediately charge a price. The price is discipline, isolation, error correction, humility in the face of noise. So let's synthesize what we've learned. Quantum advantage is not a single finish line. It's a moving frontier between mathematics, physics, and engineering. Quantum computers gain their power not by brute force, but by carefully engineered interference. And the central obstacle is decoherence, the universe constantly trying to learn what your qubits are doing, collapsing the very patterns you need. Fault tolerance offers a path forward, but the overhead is real, and more qubits only matters if those qubits can stay coherent and correctable long enough to do meaningful work. Now for a thought experiment to carry into your own life. Imagine your memories as quantum information, not in the literal neuroscience sense, but as a metaphor. The most important things you know about yourself, your values, your relationships, your purpose, are also fragile patterns. They can decohere under noise, stress, distraction, constant interruption. What would error correction look like for a human mind? What rituals, what boundaries, what redundancies protect the phase of who you are? And the next great question, the one that opens the next door. If computation is constrained by the fabric of reality, then what else have we been treating as abstract, that is actually physical, fragile, and expensive to preserve? If time itself might be an emergent bookkeeping device, what does that say about the memories we hold most dear? If you want to keep going, I'm putting another investigation on the end screen that builds directly on this feeling of reality as an information engine. Click that next, don't let the thread break. And if you want more audits like this, where we keep the wonder but refuse the hype, subscribe. I'll help you separate what's physically possible, what's technologically plausible, and what's just a good story. One question for you, simple, but revealing, when you hear quantum advantage. What's the first application you think of, and do you believe it's nearer to a stunt, a tool, or an industry?